Hello, class. Welcome to the second part of the lecture on authentication. The first part, of course, was basic introduction to cryptography. So the second part is going to now build on some of those basic constructs to build uh, authentication primitives. So these slides are going to talk about MAC, which is Message Authentication Code, HMAC, or Hashed Message Authentication Codes, hash functions, and digital signatures. These slides also contain details of SSL or Secure Sockets Layer, which is now called Transport Layer Security. But I won't be discussing them in this lecture. Rather, I will be covering that material together with the material on network protocols in the very next lecture. Okay. All right. So let's get started with these. So the goal of the lecture today is to develop what are called message authentication primitives. So the goal of message authentication is to protect the integrity of a message that Alice sends to Bob. In other words, um, the message should reach Bob from Alice. It should reach untampered. Whatever Alice intended to send to Bob, that is the message that Bob should receive. Um, Message authentication is also concerned with validating the identity of the originator, which means that when Bob receives a message from someone claiming to be Alice, he should in fact be able to confirm that the message was sent by Alice, right? That is sender authentication or validating the identity of the message sender. Uh, the third goal is non-repudiation of origin, which is typically something that you take up when you have to resolve disputes. So, for example, Alice might have sent a message to Bob sometime in the past, uh, and maybe something went wrong for Bob as a result of reading and acting on that message. Okay, so maybe Alice is dealing in stocks and shares, and Bob is a stockbroker. Okay, so Alice might send a sell message to Bob, and then Bob might act on it. Uh, but later on, maybe the share value dropped, and Alice wants to get rid of the shares, and she tells Bob, "Look, hey, I never sent you that message. You just bought it. Somebody else must have sent you that message. Uh, you're lying that I sent you the message." Okay, so in such a case, Bob must be able to prove to some independent third party, for example, some government body, that in fact Alice sent the message and he acted on Alice's instructions. Okay, so that is called non-repudiation. Non-repudiation means that Alice cannot later on deny having sent the message, and that Bob will be able to prove that in fact the message that he received was sent by Alice. So those are going to be the three security requirements that the constructs that we will develop are going to address. And we will talk about some primitives. Of course, there is message encryption, which we spoke about. We'll talk about message authentication codes, hash functions, and also digital signatures, even though they are not mentioned on this slide over here. So, message encryption itself provides a measure of authentication. Right? I mean, for example, if Alice and Bob are using symmetric key encryption, uh, then Alice knows that the only person who can decrypt that message is Bob, because only Alice and Bob share the symmetric key for the channel, for the encrypted channel between them. So the receiver knows that the sender must have created it. Of course, for all of this, the message must actually make sense. So I can send you anything. I can send you a bunch of bits. Alice can send Bob a bunch of bits, and Bob can still decrypt them, but they won't decrypt into anything meaningful, right? They might just decrypt to garbage, or the message might not be properly formatted, or something like that. Of course, we are assuming that none of that is the case, and that there is some semantics associated with the message. Maybe there is a certain structure, right? Maybe these are XML or JSON files, and that you must at least be able to preserve that structure.
So within those constraints, of course, the receiver will know that the sender must have created it, since only the sender and the receiver are sharing that key. Okay, and you also know that the content cannot have been altered. Again, over here, it all depends, right? An attacker may be able to inject a packet, but the content will decrypt to garbage, and Bob should be able to say that it's garbage. I'm talking about all of these things modulo those assumptions. Okay, so if there is a certain structure to the message, maybe you can use some sort of redundancy or a checksum to uh, detect any such changes. Uh, checksums are used to make sure that the message is properly formatted. So if you are an attacker who injects some malicious bits into a packet in transmission, and the packet is encrypted, chances are that you will not be able to corrupt both the message as well as the checksum part, and the receiver will be able to detect that something is wrong. So encryption by itself provides some degree of authentication, uh, but we want more, right? So of course, if public key encryption is used, as you remember, when Alice was sending a message to Bob, Alice encrypts the message with Bob's public key, right? So even if the message arrives untampered, of course, in public key cryptography, you'll not know who sent the message, unlike with symmetric key encryption, because there only Alice and Bob share the key. So here, in public key encryption, the receiver Bob will not really know uh, who is the sender, right? So that somebody can claim to be Alice and send the message on the same way, and Bob has no way of differentiating between the real Alice and somebody pretending to be Alice. Okay, so anybody can send such a message, but if the sender, which is Alice in this case, also signs the message or digitally signs the message using their private key. So what is that? So that is in some sense saying, look, in addition to the message, I'm also going to send you a signature, and the whole thing is going to now be encrypted with Bob's public key. What's the signature? The signature is basically that same message encrypted under Alice's private key. So if you send that message together with that signature, the signature is nothing but M encrypted under Alice's private key, and you send the whole thing encrypted under Bob's public key. Then, of course, when Bob uh, decrypts the message, he can read the message. He knows that only he can decrypt it because the message is encrypted with his public key. And he can check the signature by just decrypting the message with Alice's public key, which of course is known to him. And whatever he decrypts should match the plain text message that he just obtained. And so if he is able to do that, then you are able to get both secrecy as well as authentication. And this particular way of doing things is called a digital signature. With RSA, you can do it trivially, right? You just take the message, encrypt it with Alice's private key. Alice does that and sends it, and so only Alice could have created that digital signature. Okay, so again, you need to recognize corrupt messages, and you can do this with checksums. You can even do this with the digital signature. But of course, there are two public key users on the message, right? First to produce the digital signature, and the second one to uh, uh, to encrypt and send the whole thing under Bob's public key. Okay, so that's one way to obtain authentication with public key encryption. So now what we are going to do is look at some other constructs that are somewhat cheaper to implement, more convenient to implement, and they are widely used. They serve different purposes. Not all the primitives we talk about are going to achieve all the three goals of message integrity, sender authentication, and non-repudiation. And sometimes you don't need all of that, right? So if you don't need all of that, you can probably use a lighter weight construct. So one such lighter weight construct is this thing called a MAC, or a message authentication code. So what this does is that it takes uh, an arbitrary piece of plain text, and it generates a fixed size block. Okay, so unlike the the previous approach, which used public key or even symmetric key encryption, where the size of the ciphertext can depend upon the size of the plain text. A MAC is always a fixed size entity. Okay, so it's a fixed size block regardless of what the input size is. So you could have a terabyte video and you will still get a fixed size MAC block. So MAC depends on both the message as well as a key. Now this key is something that is shared between the sender and the receiver, just like in symmetric key encryption. Okay. However, the key thing over here is that it need not be reversible. Okay, unlike encryption where you have to have an encryption and a decryption function, a MAC can just be like a one-way operation. Okay, you apply the MAC algorithm, you get this fixed size block, and then you can check. Right, that is all is required. You don't need to be able to get the original message from the MAC. That requirement is not there. So generally speaking, what happens is that you compute this MAC on the message and you append it. I'm using the term signature loosely over here, but you append it at the end of the message as a checksum or a signature. So when the receiver gets the message as well as the MAC, the receiver performs the same computation on the message to compute the MAC on their own and checks whether whatever they computed matches whatever was sent as the MAC value. Okay, and if they are the same, then they have an assurance that the message was sent unaltered and that it is coming from the sender. Okay, so this is how it works. Pictorially, you take the message, which is shown in blue, and the MAC algorithm always produces a fixed size block, which is shown by this hatched block. The MAC algorithm, of course, takes a key. That key is shared between the sender and the receiver. So it's very similar to symmetric key encryption. But it's not encryption, right? I mean, although you can implement MAC using encryption algorithms, as we will see in the next couple of slides. So you take this MAC and you append it to the plain text message as shown there, and you transmit that entire thing. So it could be corrupted during transmission, um, and if it's corrupted, then it'll be able Bob will be able to decrypt detect it. But essentially, what happens is that when the receiver receives it, they will take the blue part, pass it to the MAC algorithm uh, with the shared key. They will get some output and then compare whatever they receive in the message together with whatever they computed, and it should be an exact match. If it is not, then they know that some corruption has occurred during transmission, either because of faults or because of malicious actions by an attacker. Either way, you will know that something is wrong. So uh, MAC clearly provides authentication, and the reason it provides authentication, so well, first of all, MAC provides message integrity, right? So if a message is corrupted, then you know that the MAC will not match because unless the attacker also has access to this key, which they don't, they will not be able to compute the MAC correctly. It also provides sender authentication because when, let's say this is Bob and this is Alice, when Bob receives the message, he has to apply the corresponding key to calculate the MAC on his side. And if somebody is claiming to be Alice and sending this message, uh, then he will use that key. So he knows that it is that key. And because the attacker is assumed not to have this key, nobody else can produce the correct MAC. So therefore, MAC also provides a sender authentication. Okay, so together with MAC, of course, you can also use encryption for secrecy. So this message over here need not be sent in the clear. You can obtain a MAC and you can also encrypt the message. So you can produce another yellow block, let's say. So the yellow block together with this hatch block are sent over to the receiver. So as shown in this picture, you're only getting message integrity as well as, of course, sender authentication. But the message need not be sent in the clear. You can also send an encrypted message. Okay, so the encryption typically will use a different key than the key that is used for computing the MAC. It will not be the same key. Um, and the MAC can either be computed on the plain text message after which the message is encrypted, or it can be computed on the ciphertext. Does not um, matter, but generally speaking, the practice is that the MAC is computed on the plain text and then the plain text is encrypted and sent together with the MAC of the plain text. That is generally considered to be the better practice. Okay, so you might ask, why even use a MAC? Well, sometimes only authentication is needed. Uh, you only want to compute checksums. Um, and you might also need to use this authentication to persist longer than encryption, right? You might want to have on record that this particular message was sent, and you might want to keep it in your archives. You don't want to store the whole message, so you just keep that fixed size block. Okay, it's very important to note that a MAC is not a digital signature. Okay, in other words, um, it is not providing non-repudiation. So, um, you know, Bob can receive a message over here, but he cannot prove to an independent third party that this message was in fact sent by Alice. Why? Because if he goes to an independent third party like a court or something like that and says, hey, Alice must have sent this message because I have the Mac, they can say, look, how can you prove that Alice sent the message? You could have created a message of like this yourself and produced a Mac like this yourself because the key K even you have in addition to Alice. So there is no guarantee over here that Alice sent the message. Okay. Or in other words, later on, if Alice disputes that she sent the message, Bob cannot really go and contest that fact, right? That is not possible. So it's not a digital signature. It doesn't give you the full power of digital signatures. Uh, but that's okay. In some settings, that is acceptable. And so uh, it is important to keep in mind that even though Mac is useful, it is not really providing you the full power of digital signatures. Okay, so it is nothing but a cryptographic checksum, right? So it condenses some sort of a variable length message, which is the whole plain text, into a fixed size block, right? It's using a secret key K, um, and it's a many to one function, right? So naturally, because arbitrary size messages are being condensed to fixed size blocks, there are going to be collisions. But hopefully the collisions cannot be engineered, right? In the sense that if I'm giving you a Mac, you are not going to be able to produce two plain texts easily that have the same Mac. Uh, and that is the collision resistance properties that you want to from a Mac function. So generally speaking, right, algorithms such as DES and AES, symmetric key algorithms, are used in something called cipher block chaining mode. I did not discuss this in the uh, uh, in the lecture, but it is there in the required readings for the class, and you should go and look it up, right? So if you see, for example, over here, the three handouts, crypto 1, 2, and 3, these handouts actually talk about the cipher block chaining mode and of using DES and AES or any symmetric key algorithm. And generally speaking, Mac is implemented as the in using CBC mode, and they just take the last block from the CBC chain, right? That's generally how Mac is implemented in practice. Okay, so it needs to take into account various types of attacks. Of course, knowing a message and the Mac, you should not be able to find another message with the same MAC. If you're able to do that, you can replace the message, send the same MAC, and the receiver will be fooled into thinking that the message is correct. So the distribution of these MACs should be uniformly distributed, right? I mean, if you think about the MAC, just to take an example, maybe it's a 256-bit string. Uh, for any given message, you should not be able to tell which portion of the distribution uh, of the all zero string to the all 256 or all one string of 250 of length 256 it will be, right? So the distribution should appear to be uniform regardless of what the input plain text is. And the MAC should depend equally on all the bits of the message, right? It's not like you should be able to compute the MAC only with some bits of the message. Then what the attacker can do is that he can keep those bits the same and then replace the rest of the message. Okay. So you can use symmetric ciphers for Macs. And as I said, one of the ways of doing this is that you use the the symmetric cipher, AES or DES or whatever, in CBC mode or cipher blockchaining mode, and you just use the final block as the MAC. So the data authentication algorithm is actually a published standard for using MAC, and it applies DES in CBC mode. So since I am talking about it, let me just explain what DES in CBC mode is. There is a diagram for this. It is not that hard. So generally speaking, DES, as you know, or AES uh, is a uh, is a, uh, block based cipher, right? So what happens in DES or AES is that you process your input message in blocks, right? So one block at a time, and let me just go and show you the picture of how cipher blockchaining mode works. So each one of these blocks over here is actually AES or DES that works on a fixed size plain text. And so as you can see, here's the plain text. You apply the key, you get the ciphertext of some fixed size. Okay. So this particular way of doing things is called ECB, or electronic code book. Now let me show you how CBC works. In CBC, what happens is that you take the plain text, okay, and you take an initialization vector. Both the plain text and the initialization vector are of fixed size, right? The block size of the encryption algorithm. You XOR them together, and then you pass them through the encryption algorithm. The encryption algorithm takes a key, and then of course it produces the ciphertext. Now that same ciphertext that is obtained from the first block is now passed on to the next iteration, where you take the next chunk of plain text, next block of plain text, XOR this ciphertext over here, and then pass that to the encryption algorithm, which then uses the same key, of course, produces a ciphertext, and it keeps going on. Depends upon the length of your plain text. Okay. Now the idea behind MAC is that you just take the ciphertext from this last block and use that as your MAC. So it has all the properties you require. It is a fixed size entity, right? It does not depend upon the size of the plain text. It's always of fixed size. It depends on all the bits of the input, because every bit of the input has been used in its computation, either directly or indirectly via these XORs, each of which is a ciphertext of the corresponding plain text, um, and it therefore satisfies the properties you want. And because you're using an encryption algorithm, you're relying on the strength of the encryption algorithm to make sure that the MAC cannot easily be reversed. Okay, so generally speaking, for DES is another popular algorithm, just like AES. You use an uh, initialization vector, this thing over here, of all zero, and then any message that is not a multiple of the block size, you zero pad it, right? You pad it with zero so that it's a multiple of the block size, and you encrypt it using the DES algorithm in CBC mode. Just send the final block, right? Uh, or the leftmost m bits. M is 16 to 64, depending upon the size of your MAC of the final block. That is your MAC. Okay. Clearly, you cannot reconstruct the original message just given this last block, but that's enough, right? I mean, MAC does not have to be reversible, unlike encryption algorithms. Okay, so we have looked at MAC, but now let's look at digital signatures, right? So digital signatures allow you to verify the sender, of course, the date and type of the signature. You can also authenticate the message contents, and you can also do non-repudiation, right? You can verify, somebody can verify by that, in fact, Alice sent the message uh, to Bob. Okay, so it's an authentication function that is much more powerful than just message authentication codes. Okay, so the digital signature must depend upon the contents of the message that are signed. It must use information that is unique to the sender, right? So something must uniquely identify the sender. Even in Mac, that's the case. Um, but that private key that is used to compute the MAC is in fact shared between the sender and the receiver. Right? In this case, in digital signatures, that will not be the case. It will be something that's unique, in fact, to the sender. So this prevents forgery by the receiver, for instance, and also denial of sending the message by the sender. So it protects both. It should be easy to produce, and it should be easy to recognize and verify, and it should not be computationally feasible to forge. Okay, and the digital signature should ideally be short. It should not be too long. Okay, so uh, yeah, so it should only receive involve the sender and the receiver. So if you assume that the receiver has the sender's public key, then the digital signature is made by just signing the entire message, or you take a hash of the message and the sender signs it with their private key. Alice signs it with or encrypts the message with her private key. Okay, uh, and of course you can encrypt the whole thing using the receiver's public key, Bob's public key, and then you send it over. Uh, and then Bob can decrypt it with his private key, and then he can use Alice's public key to then check the signature. So it's important that the message actually be signed first, and then you encrypt both the message and the signature. That's generally the protocol that's followed. So you take the message, you compute. Alice takes the message she wants to send to Bob. She computes the digital signature of that, which is the same message encrypted with her uh, uh, private key. And the whole thing is concatenated and encrypted using Bob's public key and sent over to Bob. Bob can then decrypt it with his private key and then check the signature. Okay, uh, so that allows Bob um, uh, to verify that the message was in fact sent by Alice. And the security, of course, depends upon the sender's private key. So with RSA, it's straightforward to do digital signatures as well. In fact, it was the very first digital signature algorithm. It was published in 1979, and it has become extremely influential. It won all the three authors of the algorithm, Rivest, Shamir, and Adelman. They won the Turing Award, uh, largely in part for the creation of the crypto system, which was also capable of doing digital signatures. Um, and so there you go, right? But there is another very important digital signature algorithm called DSS or DSA that is now in popular use, and we are going to just briefly look at that. Uh, just like RSA derives its security from the hardness of factoring large numbers, prime factorization. Uh, just like that, DSA, the strength of DSA comes from the hardness of discrete log. Okay, so uh, okay, so it's called DSS, the standard, and the algorithm itself is called DSA. It was produced in the early 90s. It's an interesting algorithm. It looks slightly different. We will look at it now. And it creates a 320-bit signature. I'm not entirely sure whether this is still the current standard. When I did create these slides for the first time, it was the standard. So it's a 320-bit signature with 512 to 124-bit security. What that means is that the hardness of guessing the signature is as hard as doing uh, uh, brute force attack on a 512 to 124 bit, right? So that is 2 to the power of 512 or 2 to the power of 1024 in terms of hardness. Okay, and the security, as I said, depends upon the hardness of computing discrete logs. So, okay, so yeah, this is just a repeat. Let me go to the next slide. So this is how it works, right? So this is the RSA approach. We'll compare the RSA and the DSS approach. The RSA approach is you take the message. This is Alice's side and this is Bob's side. Same thing over here, Alice's side, Bob's side. You take the message and you hash the message. You pass it over to the encryption algorithm, and Alice applies her private key. You get some output, you concatenate it. This parallel sign is the sign for concatenation. You concatenate the message and the output, send the whole thing over. Here I'm not using anything for message confidentiality, right? So the message is just being sent. Of course, you can optionally encrypt it with Bob's public key. But essentially, Bob gets this message as well as this digital signature. And what he does is that he hashes the message, and then he decrypts it with uh, uh, Alice's public key, which he has, and then he compares the output. That's the RSA approach. of digital signature verification. Okay, so in the DSA approach, you take the message and you hash it and you pass it to this function called sig, which computes the signature. So the sig takes a bunch of parameters. It takes a bunch of public parameters which are known to everyone, not just Alice and Bob, everyone. And it takes Alice's private key. Okay. The third thing it takes is that it takes this value called k, which is a random number. It is called a salt that produces a different digital signature each time, even if it's the same message. Okay. So based upon this value of k, you get a different digital signature for the same message. So you get that output and you get this message, and then you concatenate both of them and you get your output. Okay, so then that concatenated message together with the message and the signature are sent over um, uh, to Bob. The key thing about the digital signature approach is that it produces two parts in the digital signature. We will call them R and S. Okay, they're sent over to Bob. Now Bob gets the message as well as R and S, and what they do is that Bob computes the hash of the message, passes both R and S to this verification algorithm, uh, passes the public parameters as well as Alice's public key, and then the output should match. Now you will note that this K is not passed over here. So this is a method by which Alice can produce different digital signatures for the same message, uh, um, depending upon who she's sending the message to. So she can create a digital signature customized for Bob. She can create a digital signature that is customized for another recipient called Charles, and so on, right? So by just changing the value of K, and the verification algorithm does not depend upon this value of K. Okay, so you already know about discrete logarithm. So I am going to skip the discussion of the discrete logarithm and move on to the next one. So that's not going to be over here. Okay. Okay. So this is how DSA works, right? In DSA, the public and the private keys are not RSA public private keys. They are specific to the DSA algorithm. So in DSA, you have some shared public key values. That's the PUG that is written over here. These PUG public parameters. Okay, and this is just the standard, right? So the Q is a 160-bit integer, and P is some large prime that is, 2 to the power, that is around 512 to 1024 bits. Um, and Q should be a prime factor of P minus 1. So this is just the setup, right? There are some mathematics behind it. We don't need to fully understand uh, all of the details over here. And what happens is that you choose G to be equal to H to the power of P minus 1 divided by Q. Okay, and so the end users choose their private key, and then they compute a public key. So they choose a private value, um, PR of A, that is less than A, and that's less than Q, and they compute a public value, that is G to the power of PRA mod P, right? So this should remind you of discrete logarithm. So if you know the public key and you know G and you know P, it is hard to compute PR of A. Okay, so the the security of the scheme is based on the hardness of the discrete log problem, hardness of inverting discrete log. Okay, so let me now tell you about how you create the digital signature and how you verify it. So to create the digital signature, the um, um, the sender creates this random number k. It's called a salt or a nonce, doesn't matter. In fact, we'll use the term nonce quite a bit in the next lecture. Only requirement is that is less than this number q, this parameter q, and it's never to be reused. Okay, so um, you will see that there are problems if you reuse it. In fact, I want you to work that out, of course, after telling you all of the details. So the signature is computed like this. R is computed as g power k reduced mod p mod q. So R is the is something that depends on k. Okay, um, and S is k inverse. K inverse is uh, I'll tell you in a minute. It's in fact the multiplicative inverse of k mod q. Okay, so what is the multiplicative inverse of k mod q? It's the number when multiplied by k and reduced mod q gives a remainder of 1. So that's what a multiplicative inverse is. So k inverse multiplied by the hash of a message, that's the actual message, plus the private key of A multiplied by this value R that you just computed, reduce mod Q. Okay, so R comma S is the signature. That pair of integers is the signature, and that is sent together with the plain text message M. So you send this message M and then the signature R and S, and essentially to verify this signature, the recipient will compute W, which is the multiplicative inverse of S mod Q. Okay, so S times W should be 1 mod Q. So you compute the multiplicative inverse, and then you compute this value U1 equal to the hash of the message multiplied by this W more reduced mod Q. U2 is R times W mod Q, and V is equal to G to the power of U1 multiplied by the public key raised to the power of U2 mod P reduced mod Q. And it so turns out that if you compute this V and the message is not tampered, it should match this value R. If any tampering happens, this equality will not happen. And if V matches R, you say that the signature is verified. Okay, fairly complex construction, but in fact, you can verify for yourself that the proof goes through. So let's just see why V should be equal to R. It's so you know that the public key PUA is nothing but G to the power of PRA mod P. Okay, so you substitute U1 and U2 from the previous slide into the value of V. What do you get? Well, you get G to the power of HM times W mod Q and G to the power of PRA uh, times R times W mod Q. Okay, that's the public key over here. Again, when you raise that to the power of U2, it's nothing but a multiplication. Okay, and so that if you reduce, that just becomes H of M plus PR of A, the private key of A, times R times W mod Q. Okay, so that's the idea. And of course, W is S inverse. Uh, and so WS is equal to 1 mod Q. Okay, so that's the idea. And S is of course K inverse times H of M plus PRA times R mod Q. And so V just turns out to be S times K times W mod Q mod P mod Q. So S times K times W mod Q is equal to K. Okay. Um, all right. So that's how it is. And V is equal to G power K mod P mod Q. And that's equal to R. Okay. All right. So I'll give you a couple of seconds to stare at the calculation. Okay. Okay. So let's now look at hash algorithms, right? So hash algorithms are another form of authentication. We have used hash algorithms so far. I talked about hashing and so on, but let's just look at them in detail now. So hashes are another form of authentication. Um, we saw MACs and then we saw digital signatures and now hashes, right? So they are weaker than both digital signatures and MACs. So digital signatures are most powerful. They give you non-repudiation as well. Uh, Mac does not give you non-repudiation, it gives you sender authentication and message integrity. And we'll see that hashes only provide message integrity, no sender authentication, no non-repudiation. And they are extremely useful as well in many, many settings. So just like Macs, they condense the messages into a fixed size. And again, they are very similar to encryption algorithms, block-based ciphers, where they process the message in blocks. Okay, there are many popular examples: MD5, MD4, SHA-1. The latest standard, of course, is SHA-256, which is now probably going to be replaced by SHA-512. So SHA-512 basically provides a 512-bit output for any arbitrary sized inputs. So this is the diagram here. You take an arbitrary message of whatever length, you pass it to the hash function, and you get something that is of fixed length. Okay. Uh, all right. So the hash function should be able to process any size data input, should always produce a fixed size output, and it should be easy to compute. So it has a one-way property that it should satisfy. That is that it should be able to, you should be able to compute the hash easily, but given the hash, it should not be able to uh, find an x easily, such that the hash of that x is equal to the hash value. So that's the one-way property. And based upon the hash function, you also want weak and strong collision resistance. So weak collision resistance means that you should not be able to easily find y uh, and x, two unique integers, such that h of y is equal to h of x. Okay, uh, for a given x. And strong collision resistance should be that it should not be able to computationally find any pair, right? So previously weak means that for a given x, it should not be able to find a y, uh, but strong collision resistance is saying, is generalizing it to all pairs. Of course, you can always find a pair x and y such that there is hash collision, because a hash is taking arbitrary size messages and reducing them to a fixed size domain. So there will obviously, it's a many to one function. There will be collisions. The point here is that it should be computationally infeasible, right? It should be a hard problem to do it. Okay, so you will see, as I said, there is quite a bit of similarity in the evolution of both hash functions and block ciphers, and you will see that there is some similar structure also in how these things are created. Again, the science of how these things are created is beyond the scope of this course, but you should at least be familiar with it. So all the readings that I have got for this course talk about the structure, but why are they designed that way is not something that we will study in this course. A crypto course, in fact, a course on symmetric key cryptography is one that will actually talk about the rationale behind these constructions. Okay, and they also use this iterative structure. As I said, in a five-step structure, you have this substitution permutation networks that are repeated multiple times in this five-step network. Just like that, you have a sort of an iterative structure for hash also. So I'll show it to you. I'll just flash it. This is not something that you have to study or understand deeply, the structure of the hash function. You should know the black box behavior of a hash function though. In other words, you should know when to use hash functions, when to use max, and when to use digital signatures. But I don't expect you to understand the internals of a hash function and how it works. Okay, so MD5, it's no longer in use, but it was designed by Ron Rivest, the same guy who did RSA as well, and it produces a 128-bit hash value. And I'll show you how it works, right? So you can actually go and read up the whole thing if you just Google RFC 1321. Okay, so here's how it works. You take an arbitrary size message and you pad it so that the length is 448 mod 512. That is when you uh, divide the message by this number 512, the remainder should be 448. And then you append a 64-bit value to the message. Okay, so you initialize a 4-bit, a 4-word, which is 128-bit buffer, and you process this message in 512-bit blocks. So 16 word is 512. Okay, and then the final buffer, whatever you get, is the hash value. I'll show you the diagram. So here's how it works, right? You take the message, you add the padding over here, right? uh, and then you process it 512 bits at a time, and the MD5 algorithm just takes an initial vector which is pre-specified. It could be all zeros or whatever like that. It's 128 bits, and then each one goes to the next. It's like a block cipher, right? So it processes the message in blocks, 512-bit blocks. So the output is 128 bits, goes to the next one. That and the input message are combined, goes to the next one, and so on. Okay, and finally you get the output over here. That's your hash value. So what are each one of these MD5 blocks over here? How do they process this 512-bit message? Well, like this. So each round has 16 steps of this form, where you take the message and split into ABCD, and you sort of iterate it. I'll show you the diagram. It's probably a better explanation of this slide over here. Again, this is just for your information. You're not expected to sort of memorize this structure or analyze this structure in any way, right? This is just for your information of how hash function works. So this is basically how it works. So you take that 512-bit message and split it into these four parts, these so-called buffers, and then apply a fixed function, and then it goes through a sequence of steps, and what you get is another four buffers, that A, B, C, D, permuted in some order with these functions applied, as you can see. And the same thing is iterated multiple times, 16 steps, right? So each word is updated and then 16 times, and then you get the output. That's what each one of these HMD5 boxes is. Okay, and that's applied to every 512 bits, and this 128 bit buffer is also part of the input. Okay, so that's MD5. Now MD5, actually there are known attacks. In 2004 itself, it was broken. Somebody was able to create collisions for MD5. So it's no longer actually in wide use. Nobody uses MD5. Uh, right now it's all replaced by the SHA family of hash algorithms. Uh, SHA stands for Secure Hash Algorithm. Okay. Uh, and 256 is in wide use, but it is probably going to be replaced by 512-bit hash values, SHA-512. Okay, so I'll just tell you how SHA-1, a little bit about SHA-1. So SHA-1 produces 160-bit hash values, and it's generally SHA family is the preferred one now, although SHA-1 is not in use. SHA-256 is in use. SHA-512 will come soon. But it's evolved from MD4 with some key differences. Okay, again over here, this is just for your information. It's an algorithm quite similar in structure to MD5. These are all things that are evolved by the National Institutes of Standards and Technology through public competitions. Okay, um, so exactly why these things are initialized in this way, why the message is patterned in this way, and why the initial vector ABCDE are set to these, um, they are questions that NSA or NIST can best answer, right? But this is what the initial parameters as specified in the standard are. Okay, and it produces an output that's 160 bits long. Okay, 256 produces 256-bit values, and 512 produces 512-bit values. You can try all of this, right? So you can actually um, do it on your Linux machine. You can create a hello world file um, with whatever contents you want, and you can actually compute MD5 hashes. So this is the MD5 hash of hello world. uh, this is the SHA-1 sum. You can actually confirm that this is 160 bits, right? Each one of these things is 4 bits, and you'll find that there are 40 such elements over here. So that's uh, a, uh, a 160-bit value. Okay, SHA-256 is SHA-256 sum, SHA-512 is SHA-512 sum. It's easy to compute it on the command line. Okay, so the brute force attack is much harder because you have many more bits. And so every time you add a bit, the idea is that at least technically the effort to do a brute force attack doubles because you're adding one more bit. Um, it's a little slower than MD5. I don't think that this statement, not vulnerable to any known attacks, is still true. People have also come up with attacks on earlier versions of SHA. And that's why SHA-512 is good, because now it's 512 bits, and so um, the brute force attack gets that much harder. Okay, so now that we have spoken about hash functions, in fact, there's a very easy way to compute max using hash functions alone. You don't have to use any symmetric key algorithms in Cipher blockchaining mode, there's a very easy way to do max using hash functions, and those are called hash max or HMax. So it's as simple as this. You just take the message, and as in max, you also have a key, but then you concatenate the message and the key. Maybe you do an XOR or something like that, and then you hash it, and that's your keyed hash. Okay, so that's called HMAC, but there's a standard, right? This is just a ad hoc way of doing it. There's actually a standard for HMAC, and this is the way you do it, right? You take a hash function. It only you can compute this MAC using a hash function alone. No Cipher algorithms. So there is an initial padding vector and a key. Of course, you take this, uh, and then you take the initialization vector, pass it to a hash, um, and you get your hash message, you pad it, and then you produce the HMAC of it. There's a standard for this. I'm not going over the structure of it, but what I'm essentially trying to get at is just using a hash function, it is possible to create a MAC, and those are called HMACs. And as you can see over here, this is a MAC that depends only on the message M, this key K, as well as a hash function. No encryption algorithms are used. So this is an easy way to produce MACs using hash function. And even though the structure here is somewhat more complicated, you can think about it as applying some fixed function to the key and the message. Over here, it's just concatenation, but some fixed function to the key and the message, and applying the hash function, and then you get the output. That's called a hash MAC or a keyed hash. Okay, so again, if you want to learn about the HMAC standard, that's RFC 2104, and this is the exact way in which you compute the HMAC, right? Here's the message, and there is something called an input and an output pad that's XORed with the key, and then you hash it, and then you concatenate it in this particular way, right? Message concatenated with this stuff over here, hashed, again concatenated again with this stuff over here, which depends upon the key, as well as a fixed input and output pad and the hash function. Okay, and k plus is nothing but the key that's padded to a fixed size. So the padding is always deterministic. You add uh, a uh, a few more bits at the end in a pre-specified way. Okay, and the advantage here is that you can use any hash function and you can get a corresponding HMAC by just doing that. So it's much cheaper than using something like TESS or AES in Cipher blockchaining mode. uh, Hash functions are generally supposed to be much faster. Okay, so the HMAC, the security of the resulting MAC depends on the robustness of the underlying hash algorithm, and HMAC requires, so if you want to attack the HMAC, it requires either a brute force attack on the key used, or there is something called the birthday attack, where you use the birthday paradox to try to identify collisions, but those are pretty hard as well. Okay, so just to summarize, here are the various ways to do message authentication, right? You can of course use conventional encryption, um, and you can use public key encryption. You can use a MAC, right? Um, of course, so this particular way I didn't tell you about, but it's fairly simple. Take the message and then you apply a secret nonce over here, and you compute a hash, and then you just send the message and the hash over here. You append that secret that both these guys know, and then you compare the result. Um, so that's message authentication, and that brings me to the end of this lecture. As I was mentioning in the beginning of today's lecture, uh, the set of slides that are posted on the class webpage also has secure sockets layer, which is transport layer security. That will be covered as part of next lecture. Okay, so we will stop here for today. This is the second part of our uh, uh, of the lecture on authentication primitives. Okay, so uh, in the next lecture we will talk about network protocols.